let's take a look at more equations describing simple harmonic motion. And we'll start out with an equation to describe displacement. And we'll start out with the most bland equation we can think of. Let's just have a sine graph that looks like this. And if we do, then x, the displacement, would equal the amplitude of the motion times the sine of something. What goes in there? What's the something? That's the question. Well, it can't be that x equals x0 times the sine of t. It can't just be t as the argument of sine. That wouldn't give us the right period. If we did this, well, sine repeats every 2 pi radians. So if we did this, then this is just a graph that repeats itself every 2 pi, no matter what. And that's not necessarily the period. So a better one would be x equals x0 times the sine of 2 pi t over the period. If you think about it, this is good. This repeats every time t equals a period, or a multiple of a period, right? Because every time t is equal to a period, then we get sine of 2 pi. So there we go. The equation repeats itself. The graph repeats itself. Notice that we can rewrite this because 2 pi over the period is equal to the angular velocity. So we can also write this equation as x equals x0, the amplitude, times the sine of omega t. Now, there's another reason why we like the angular velocity. It makes this descriptive equation for the displacement a little neater, right? It's better than 2 pi t over t. Now we just have omega times t. But we can generalize this a little bit more. That equation only applies if the oscillating object is at equilibrium and with a positive velocity at time t equals 0, which is not necessarily the case in every single oscillation we can think of. We can shift this, though, using a phase angle. And I'll show you what I mean. A more general equation would be that x is equal to x0 times the sine of omega t plus phi, where phi is the phase angle in radians. So for example, if we have a graph that looks like this, like a cosine graph, that's really just that original bland sine graph shifted to the left by pi over 2 radians, by a phase angle of pi over 2. So we can just rewrite the equation with a phase angle, where we can describe this new equation, or this new graph, using the phase angle. The oscillation will be at equilibrium with a positive velocity at a time t equals negative phase angle over the angular velocity. All right. Now, it's a little tricky. Maybe you think that this isn't the simplest possible method, but it does work. Now, with a little bit of calculus, we can get a couple other equations. So let's say that we describe the displacement as amplitude times sine of omega t plus phi. Well, the velocity would be the derivative of that displacement equation. So if you take the derivative of it with respect to time, well, okay, d by dt of x0 sine of omega t plus phi. Well, x0 is a constant, so we can take that out front if you know about derivatives. So it's the derivative of that. Okay, we'll take the derivative of that, do a little chain rule in there. So v is equal to the angular velocity times the amplitude times the cosine of omega t plus phi. That's an expression for the velocity. And let's go one further. Let's get the acceleration. Take the derivative of velocity, and you get acceleration. So we do that. And let's see, what would we get? We would get negative amplitude times omega squared times the sine omega t plus phi. All right. Well, just so you know, x equals the amplitude times sine of omega t plus phi, and v is equal to omega x0 cosine of omega t plus phi. Those are in your data booklet. So those are general equations to describe the oscillation in simple harmonic motion for the displacement and the velocity. And we got that bonus acceleration equation. Let's look at that for a moment. We can take that acceleration equation we got, and guess what? That amplitude times the sine of omega t plus phi, that is the displacement. So I can replace that with the displacement, and look, there you go. There's the governing equation for simple harmonic motion. Pops right out. Now, notice that those equations all depend on knowing the time. So you can get the displacement, you can get the velocity, if you know what time you're talking about. But what if you want to know the velocity at a certain location? What if you want to know the velocity not at a given time, but at a given position or displacement? Well, there's an equation for that. I'm not going to derive it right now, but v is equal to plus or minus the angular velocity times the square root of amplitude squared minus displacement squared. All right, so seems like that comes out of nowhere, and there's a little bit of thinking we got to do here. So if you know the displacement from equilibrium, and you know the amplitude, and you know the angular velocity, this equation tells you the speed at that displacement. Now there's a plus or minus in there. Why? Well, if we think about it, let's think about the displacement versus time graph. All right, so we got it looking like this. Let's get that bland displacement graph. Well, if I want to know the velocity at a certain displacement, let's think about a certain displacement here. A certain displacement would be like along this horizontal line here. If I want to know the velocity when it's at that displacement, well, it could have two possible velocities. It could either have a velocity that's positive or a velocity that's negative. That's why we have the plus or minus. At every displacement, at every given displacement of the oscillating object, the velocity could either be positive or negative at that location. It depends on where it is or when it is in its oscillation. And now let's look at energy. So if we're thinking about an oscillating object, the oscillating object would have two different types of energy at any given time. It could have kinetic energy and it could have potential energy. Kinetic energy, that equation, okay, it's just 1/2 mv squared. The potential energy, well, that's a little trickier. If it's a mass on a spring, it's given by 1/2 kx squared. But in general, the potential energy in an oscillating system would equal 1/2 m times the angular velocity squared times x squared. And I'm not going to derive that right now. It can be derived, but just know that that's the case, and that's in your data booklet. That equation is. Now, the energy goes back and forth as this thing oscillates. It goes back and forth between kinetic energy and potential energy. But no matter what, the total energy that this thing has is equal to the kinetic energy plus the potential energy. Right? Those are the two types of energy it can have, so the total energy is the sum of those two at any given time. Well, so then the total energy would be equal to the potential energy when the potential energy is at its maximum value and the kinetic energy is equal to 0. And so the greatest that the potential energy can be, the maximum value of the potential energy, is when it's at a displacement equal to its amplitude, when it's at those extremes of the motion. Because that's when the velocity is 0, right? And it has no kinetic energy. And that's when it's furthest from equilibrium, so it has the greatest amount of potential energy. And an equation for that, if we look at that last equation we had, the total energy then is equal to 1/2 m angular velocity squared times the amplitude squared. All right. Now, we could also write this a little bit differently, right? If we think about it differently, the total energy is equal to the kinetic energy when the kinetic energy is at its maximum value and the potential energy is at 0. Well, let's think about it. Okay, the kinetic energy is at its maximum value when we have 1/2 mv squared and v is maximum. Okay, well, v, the maximum that v can be, if we look at our v equation, v is equal to what? Omega x naught cosine omega t plus v. The greatest that this can be is omega times x naught. So let's plug that value in. That's the maximum value that v can have. So then we have 1/2 m omega x naught quantity squared. And so we get that the greatest amount of kinetic energy they can have, which is the total energy, is equal to 1/2 m omega squared x naught squared. The same thing that we had before. And that equation for the total energy is in your data booklet.